Okay, so let's go to this. I'm going to go over some history here. So basically, the objective is that so what kind of geometric projective structures are on so given force or manifold? So this is a naive question, but anyway. So and then second is to determine the topology and geometry of deformation spaces. So take DM and then look at all the geometric or projective structures on M, and then you quotient by the isotopies. And these are locally, you can consider these as character spaces, such as home pi 1 M, PGL, and R, n plus 1 R quotient by the conjugation, and the home, or you can do it for SL plus minus 1 n plus 1 R too. So for other geometric structures, there, of course, be other G's here. Of course, there's a parenthesis missing here. Anyway, so that's basically what we are going to do. So because in the like for the lattices, you determine that these are sort of points. So if these are not rigid, then what kind of things exist and that kind of things. Um, so how do you consider these geometry from the geometry and topology point of view and the algebraic point of view and so on? So so if you can use the theory of manifolds or bifold, is it going to be easier to understand? Okay. So so after these rigid type of geometric structures were studied much, and then you can one should consider these sort of flexible types. So those are conformally flat, projectively flat, or affinely flat geometric structures. So for example, hyperbolic three manifolds will be rigid. So these will have only one point there, and because of the Mosto rigidity and these kind of things. So, but for the conformally flat, there sometimes it's not rigid, and projectively flat is not rigid, and not always. It's mostly rigid actually, but we'll explain that later. But for conformally flat, it will be much more rigid here, and of course the existence is not that clear too, right? Right. I mean the yeah. So basically, we can kind of go back to Cartan. So he defined the projective flat structures on manifolds as geodesically Euclidean, but with no metrics. So you can characterize this as torsion-free, projectively flat affine connections on manifolds. Okay, so projectively flat means it has the same geodesic structures as the flat matrix. But of course, up to parameterizations. Okay, so those are so these are already considered in those times. The Chern was actually the first one to really study projective differential geometry and so on. The Ehresmann identified these structures as having a maximal charts of atlas to RPN with transition maps in PGR n plus 1R. And so Kuiper first studied the cross-convex projective structures on the surface of negative order characteristic. So he showed that the boundary omega is strictly convex, and each cross curve is realized as a cross projective geodesic, and so on. Okay, so those are his first, so one of the first works in there. And most of the examples of projective manifolds are by taking portions of domain in RPN, omega in RPN by discrete subgroups of PGL n plus 1R. And so domains are usually convex, and we call the quotient convex projective manifolds or bifolds. These are, of course, projective manifolds that are there are of course some projective manifolds that are not from domain. So the ones I mentioned, like these obtained from these growing many annuli in a weird way. So of course those are the first done by Goldman or even before that by Nagano and Yagi. Actually, they classify the affine two manifolds first. So some people in complex geometry study lots of these kind of things. And Hn is a interior of an ellipsoid, and Hn is a hyperbolic space, and odd Hn is a isometry group. So Hn mod gamma has always a canonical projective structure. Okay, so they correspond to. And then the Benjikri made the study of these from the point of view of convex bodies, and so that's how we proved that the boundary should be C1 epsilon. Okay, so those are and then if you C2, then it's actually ellipsoid. So those are only for the closed manifold case or closed orbifold case. And then Kusul showed that so for these are usually in the reference bibliography at the last part here. And so Kusul showed that convexity is preserved if you want change the projective structure by a small amount, it will still be convex. As long as you start with properly convex one, then it will still be properly convex. But if it's not properly convex, it's not true. But I'm just talking about the proper convexity here. And Binberg studied the reflection group acting on properly convex cones. So classify these using Cartan matrices, and these include the hyperbolic reflection groups. So there are many examples of these type of things which are not necessarily hyperbolic, but and then the Katz and Binberg was the first to find the example of a convex projective surface that is not hyperbolic, and it's based on Coxeter group. So these they study these by the linear actions. So the group is even integral group, matrix group, and then the finite. So this will give you a Coxeter 2 orbifold, and then you get a finite cover will be a cross surface, and these are not hyperbolic. Okay. So the way to show it's not hyperbolic is to show that these matrices are not symmetric. Okay, and then it follows. So see the Goldman's book for some expositions of these. Okay. And so there are some orbifold with three confinements. So for example, this will be some Coxeter group but this is actually ellipsoid. But something like this will have a confines of order 5 here, and then there'll be 6, and I think these are 6, 5, 6, 6, and then it will have a little bit. So in particular, this looks a little bit not like the ellipsoid. Okay, so those are some examples. Okay, and then more recent developments. So the Kobayashi showed that these are peninsular metrics. So how do we do that? So it's very similar to how we did it for the complex geometry. So you take some interval L is some interval in RP1, and then you map it to M. So this will define a pseudo metric. Because any interval has a you can use this cross ratio to define a metric, and then you look at all the maps into it, and then this will give you a norm. Because so for each vector you define some so these lines that send this vector to so a vector in L to this vector, and then you compare the norm, and then you look at the minimal such length for the vector, and so that will give you a peninsular metric here. So then the Kobayashi metric is a metric if and only if there's no complete affine line. So if L contains a complete affine line, then these lengths could become 0. Okay, because L can become I mean the image of L can become bigger and bigger, and then the norm is going to go to 0. Okay, so that's so this is very similar to what happens in complex case also. And so as long as omega is properly convex, there is no complete affine line, so you define a good metric. So this is a Pencil metric and equals the Hilbert metric in this case. Okay. So that's work. And it's also related to affine differential geometry. And so you take a projective structure on manifold, then it gives you an affine structure on M times R because you take any convex domain omega, then there is always convex cone on Rn plus 1. Okay, it's corresponding to this domain, and conversely, any convex cone, you can get a convex domain like this. Okay, so this is in general true. So for real projective structure, you can always get a affine structure by making any open sort of patch. Open chart into cone. Okay, so open chart in M, you can make for something small, then you can always do that. And of course, this is true for the manifolds as well. I mean, OV-folds as well, manifold and OV-folds. So affine sphere is a complete hyperspace asymptotic to omega and the affine normal line passing through the origin. So what affine sphere is that this omega will correspond to some cone, and then this hyperspace, it will be asymptotic to omega, means that the boundary of the hypersphere will converge to the boundary of omega, and then so this sphere will be convex, and then for each point you can define what's called the affine normal line. Okay, so affine, and this is just defined using the some sort of mass center of the mass and the idea, and then because these are all you can right at the because this affine transformation will preserve the center of mass things here. So then you can define this affine normal, and then the affine normal, if the affine normal passes through the origin, then it's called the affine sphere. Okay, so affine sphere structure on a cross manifold means that M tilde embed to an affine sphere asymptotic to some cone corresponding to some convex domain omega, and the deck transformation will act as a discrete linear group. Okay, so that's the affine sphere structure. And so Loftin showed that using Calabi and Cheng Yao's work on affine spheres, that if M is a closed projective plane manifold, then M is properly convex if and only if M admits a affine sphere structure on Rn plus 1. And so CP Wang showed in 70s that in dimension 2, a conformal structure on an affine on an oriented surface S of genus 2 and the holomorphic section of K3 determine an affine sphere structure on S. So K is this complexified tangent bundle. So tangent bundle will define a line bundle over there in the complex sense. So if you take a holomorphic section, that corresponds to this structure in this dimension 2 only. So this shows that the deformation space of convex structure admits a complex structure which is preserved under the moduli group action. So this is shown by Loftin, and also Loftin worked out the Mumford type complexification of modular space of convex projective structure. So what he has to do is to say these have some volume limit, volume bound, and then under the volume bound, the subspace which has this volume bound will have a Mumford type compactification of the modular space. Okay, so the Mumford type compactifications are just that you always. So the ideal points are just a set of singular points, a simple cross disjoint set of disjoint simple cross curve, which become very, very short. So for each pair, each set of these disjoint simple coarse curve, you get an ideal point. So this is a discrete set. So that's the Monfort-type compactification, and so of course, so he also found some new metric using harmonic maps. But there are now some other types of metrics which are by Peterson type pressure metric developed by Bresman and Canary, and also there are also other type of metric, but these are still very mysterious what the relationships are really, even for dimension 2. So so there are some unanswered questions here in the Cheng-Yao theory. And the next thing is the gauge theory and the projective structures. What's the relation? So Atiyah and Hitchin studied the self-dual connections on surfaces. So of course these were first studied for 4 manifolds because that has application to physics, and but they can also do it for 2 dimensions. And so Collette showed that the flat connections for manifold can be realized as harmonic maps to certain symmetric space bundles. And so, for example, if you look at the Teichmuller space, so these are the hyperbolic structures on omega made up by isotopies. So you can think of this as a component of this representation to PSL2R made up by the conjugation. So here plus means that these are the completely reducible representation, which means so whenever you have invariant subspace, there's has to be some complementary invariant subspace. Of course, that's not always true, right? So if you look at all those representation only, then this is actually a component. Okay, so that's what Bayer proved, and so then the Hitchin did was you look at gamma, which is Fuchsian group, and then you can embed it into some Lie groups, G, which is semi-simple, for example. Then this will give you a component, because so this is a component. Okay. So of course, I mean discrete Facebook component here. So that's you can identify with Teichmuller space. So there's this Teichmuller space, and then if you compose it, then this gives you a component here. Okay, so that means you can show that this Teichmuller space goes embed into this space. Okay, so that's called the Teichmuller component. Okay, so because this is connected, you get a connected component. Okay, so then and then the Hitchin used the Higgs field on the principal G bundle over surfaces to obtain parameterization of flat G connections on surfaces. So G has to be some sort of real split form of a reductive group. So in the 90s. So of course this list is not that big, but so Higgs bundle is just a pair of some B, which is holomorphic vector bundle, and V is a holomorphic section of N V tensor K. So K is a tangent line bundle, which I said before. And then so these are just endomorphism valued one forms. You can think of these as this. So NB means the endomorphism of B to itself at each point. Okay, so you collect that, and then you get another bundle. So then if you have a flat bundle on the Higgs bundle, so to find a flat connection on this V, then you have to solve for this equation. Okay, so flat connection for G. Okay, so you have to. But here, this V is a holomorphic vector bundle, so it has some orthogonal metric and then this holomorphic section. So you can reduce this finding flat connection to this equation, and then you can solve this equation, and then Hitchin Teichmuller component is homomorphic to cell of dimension 2G minus 2 dimension GR. Okay, so GR is the real part. I mean, I don't have to say GR, but you can just say R. But I'm just saying, emphasizing it's a real group. And so, so essentially you need to then take some uh, so solving this equation because this only depends on this f. So whatever f phi is, you can solve for f. So that's why it's phi is a holomorphic section. So it means you can choose whatever you want. Okay. So so for n bigger than equal to 2, you can show that it has 3 components if n is odd, and then 6 components if n is even, and so on. Uh, uh, right. So of course, I don't mean the Teichmüller component will be just one of these. So home plus will be the set of reducible ones. So he can also show this. So of course, Hessian Teichmüller component is homeomorphic cell because of these things. And additionally, he did this, right? Okay, so that's another thing. And then we do the topologist approach here. Right. Actually, so maybe we should end for today. I will continue next time because it's probably too might take too long a time, right?